Boldly going where no science show has gone before. The Naked Scientists.
Hello, coming up this week, a new breakthrough in melanoma. Scientists have found the stem cell that could cause the cancer to spread. Also, how a genetic test could soon be on the cards to tell you if you'll live long enough to receive a telegram from the Queen. And what one of the world's most powerful lasers is now revealing to scientists about the inner workings of atoms. That's all on the way. Hello, I'm Chris Smith. Welcome to this week's Naked Scientists. And also here to help me with the show is Kat Arney. Hello, Kat.
Hello! Also this week we're looking into the science of one of nature's most awesome displays of power, the volcano. We'll be talking to one researcher who's drilling into a recent eruption site, that doesn't sound terribly safe to me, to understand the processes that power volcanoes. We'll also hear how gravity can be used to effectively weigh a volcano to watch as it fills up with magma. And in a rather explosive kitchen science, Ben's been getting his hands dirty.
Now, you seem very well prepared. You've laid out lots of newspaper and you're wearing a poncho, so obviously this could get quite messy.
Don't do this indoors.
And you can find out what Ben's been up to, and let me tell you, it involves making a gas bomb with wallpaper paste later in the show. Chris.
Thank you very much, Kat. So, if you have a question for us, the email address is chris@thenakedscientist.com, or you can send us a tweet to @nakedscientists.
Laying the facts bare. I say. The Naked Scientists.
This is The Naked Scientists with Chris Smith and with Kat Arney. First up, let's take a look at what's been making science headlines around the world this week. Kat.
Yes, in the world of cancer research, there's growing evidence for cancer stem cells. These are rogue stem cells that fuel the growth of tumours. And when they divide, cancer stem cells produce new stem cells, and they also make bulk tumour cells. And treatments like radiotherapy and chemotherapy, they kill off these bulk cells, but they don't touch the stem cells. So they carry on growing and the cancer comes back. Now, stem cells have been found in many types of cancer so far, including breast and bowel cancer and leukemia. And now researchers at Stanford University School of Medicine in the US have found them in melanoma. That's the most dangerous form of skin cancer. And their research was published this week in the journal Nature.
So how did they track these cells down?
Well, led by Alexander Boyko, the researchers were studying the protein molecules on the surface of cells taken from melanoma samples, and they found that between 2.5% and 41% of cells in these samples had a protein called CD271 on their surface. And using a technique called flow cytometry, they were able to separate out cells carrying this protein and test their properties.
But how do you actually separate out a cell that's just got one of these things on its surface? Sounds tricky.
You use a magic machine called a flow cytometer, and you can do that. And then the researchers transplanted these human melanoma cells into mice, and they compared cells that carried the CD271 with cells that didn't have it. And they discovered that the cells with this CD271 were much more likely to grow into tumours than cells without the protein, suggesting they might be the stem cells they were looking for.
But there's a lot more to a stem cell than that, so how do they actually know they were dealing with a stem cell?
Well, this is the clever bit. When the researchers analysed cells from tumours grown from the CD271 positive cells, they found a mixture of human cells. Some carried the protein and some didn't. So this told them that these stem cells were not only making more stem cells carrying 271, but making bulk tumour cells too that didn't. And that's a classic giveaway of stem cell behaviour.
But it's one thing to identify a stem cell, it's another to offer a tangible benefit to patients. The rates of melanoma have gone up by about 100% in 10 years. So where does this leave us clinically in terms of therapies?
Well, for a start, the discovery of these stem cells does help to explain why many melanomas don't respond to immunotherapy. This is a treatment that harnesses the patient's immune system to destroy cancer cells. And the team discovered that the melanoma stem cells don't have certain proteins that are targeted by current immunotherapy approaches. So the body's immune system just can't see them and kill them, and so the cancer comes back. But now we know that these stem cells carry this protein, CD271, and the researchers can start working on treatments that target that, or other proteins that are specific to these melanoma stem cells, and that could lead to really powerful treatments in the future that are so urgently needed.
Indeed. Thank you, Kat. Well, assuming that the melanoma doesn't get you, what are your odds of living to be 100 or more. There's a very interesting paper published in Science this week. It's by a group of researchers at Boston University, Paola Sebastiani and her colleagues. And what they've done is to narrow down the genetic causes that could be leading to this. Now, scientists have known for a long time that old age and the ability to live to an old age tends to run in families. If you look at certain families, you will find an excess of people who tend to be very old. They'll live to be more than 90 and maybe even more than 100 routinely in those families. And this strongly suggests there has to be something genetic to this. What this group did was what's called a genome-wide association study. What that means is they took a very big group, more than 1,000 people who had lived to be more than 100. In fact, the oldest person in their group they looked at was 119 years old, and they compared those people with just under 1,300 individuals who had died about 75 years of age. So what they were able to do was by screening through the genetic material of these individuals, looking for something called SNPs, or single nucleotide polymorphisms. These are like genetic markers or signposts in the genetic material. And what you do is you look at a large group of people who have a certain trait, and then another group of people who don't have a trait, and you see if some of these SNPs, these markers, come up more often in people with the trait than those without. And that tells you that in those regions where those markers are, there are probably genes that have something to do with the trait that you're interested in. And when they did this, they found 150 of these genetic markers pointing at people who tended to be very, very old, in other words, have the ability genetically to live into a ripe old age. And by putting all of those together, they were able to derive a genetic test which would predict with 77% accuracy whether or not someone taken at random would have the likelihood, genetically speaking, of living to be more than 100.
So, what use actually is this, apart from helping the Queen to maybe plan when she has to send those telegrams out?
Well, why this is interesting is that this indicates what some of the key gene players are in the ageing process. Until now, ageing has been something of a black box. We understood some of the mechanisms. We didn't understand what genes help to defend us against the ageing process and mean that some people, therefore, can take the wear and tear of life a bit better than others. This new study means that now we can identify some of the genes which are responsible, ask what do those genes do and what is their contribution, and how do people who carry certain genes fend off the ageing process better than others, and therefore perhaps come up with better ways to make people age better or stop people getting certain diseases that they would otherwise get prematurely.
And hopefully they can come up with a treatment that you can go in the room and remember what you went in there for. Anyway, from ageing to saber-toothed tigers. I love this story. This is my favourite story this week. Far from being cute kitties, saber-toothed tigers are lethal hunters. They were roaming North and South America until about 10,000 years ago, searching for bisons, camels and other rather unfortunate prey. And today we know them for their supersized teeth. They had exceptionally large canines for tearing into their prey. But now new research published in the journal PLOS ONE suggests that there's more to these feline killing machines than their teeth.
And what's that?
Well, this is work from Julie Meacham-Samuels and her team in the US who've been looking at saber-tooth fossils. And they noticed that the saber-toothed tiger canine teeth are actually oval in cross-section. If you cut through them, they've got an oval shape. Unlike modern cats, whose teeth are actually round if you cut through them in cross-section. Now, having oval teeth actually makes them quite vulnerable to fracturing and breaking. If you try and take down an animal and it wriggles around, you're quite likely to break your teeth. And that's not a good thing for a hunting cat. And this led researchers to think that maybe saber-tooths killed their prey in a different way to modern cats, and maybe didn't rely quite so much on their impressive teeth.
And so how did they go about finding out whether that's true?
Well, they measured bones from the forelimbs of saber-toothed tiger fossils and compared them with 28 other cat species that are alive today, from a tiny cat to a tiger. And they found that the saber-toothed limbs were much chunkier and stiffer than expected, with prominent muscle attachment sites on the bones. And this suggests that they were actually, bruisers. Saber-toothed tigers had exceptionally powerful and strong forelimbs compared to today's cats.
So they're sort of more Newcastle cats than sort of southern softy cats. But how does this affect their methods of hunting and killing things then?
Big Popeye cats, yes. The scientists think that saber-toothed tigers may have actually used their muscular forelimbs to immobilise their prey before biting into them. This would really have protected their vulnerable teeth and built up their arm muscles even more. Now, today's cats have stronger teeth and relatively weaker forelimbs, so they probably rely more on their teeth for hunting than their ancestors did.
Well, talking of ancient things, even older than a saber-toothed tiger, is arguably the world's first and oldest example of a multicellular organism. In other words, an organism which is formed from more than one cell. When life got going on Earth, the first things to colonise the Earth were bacteria, just single cells. But at some point, something happened that meant that cells began to team up and cooperate together to form groups of cells that work together. In other words, multicellular organisms like us. But where did the first one come from? It could be that it evolved in what's now Gabon in Africa. There's a paper in the journal Nature this week by Abder El Albani from the University of Poitiers in France, and he and his colleagues describe an organism which looks a bit like a fried egg, actually. It's about 1 centimetre across. It's got a central core or a yolk-like structure, and this is surrounded by a flat sheet of tissue, which is itself then divided by these radial cuts that come in from the periphery into the centre, and it appears from the structure of the fossil to have been adding tissue around the edges, so growing the white of the egg outwards. And the scientists also chemically probed the fossil, and they found that there are signs of a chemical called stearine in there. And stearine is a substance which is derived from sterol, which is a chemical used in eukaryotic cells, in other words, advanced forms of cells, which are in, say, our bodies and plants and the animals around today. That is regarded as a hallmark of eukaryotic or advanced cellular life, suggesting that this organism was a fairly advanced organism. Also, the iron that the organism contains suggests that it was also aerobic. It was using oxygen in its metabolism. And this is interesting because its point of origin, about 2.1 billion years ago, is some 200 million years after something called the Great Oxidation Event. And at the Great Oxidation Event, suddenly the oxygen levels on Earth began to rise very dramatically, suggesting that this organism was one of the earliest multicellular aerobic life forms. Now, obviously, it's going to take a little bit longer to work out exactly what this thing was, what it was doing, and also to find out where it came from and what it turned into. These fossils are rare because the rocks are rare, 2.1 billion years, but at the same time, an amazing discovery because it means that now we have some kind of handle on how life as it is today got going in the first place. Now, also this week, researchers in America have used a very powerful X-ray laser to strip away the electrons from an atom of neon. But they also have been able to very carefully strip away only those electrons which are closest to the atom's centre, creating, if you like, the atomic equivalent of a cored apple. Dr. Linda Young is a Distinguished Fellow of Argonne National Laboratory, which is just outside Chicago, and she's with us to tell us how it works. Hello, Linda.
Hello.
Welcome to The Naked Scientist. Do tell us, if you could, first of all, what is this laser and why is it so special?
This is the world's first hard X-ray free electron laser, and it produces X-rays that are about 1 billion times more intense than any other X-ray source before. The intensity is actually equivalent to taking all the sun's radiation on Earth and putting it into 1 square centimeter. So it's an exceedingly powerful X-ray laser.
Obviously, you wouldn't use this clinically, but you can use this to probe things like atoms at very, very high resolution. So tell us how you're doing that.
Yes, that's right. Because this laser is so intense and all these photons come in such small bursts, you are in fact able to capture motion on the atomic molecular scale within femtoseconds. This is about the time that it takes for molecules to vibrate within, larger structures such as proteins. But because we had such an intense laser, and it's the first time anyone had it, one really wants to understand how that very intense X-ray beam interacts with matter. And so you might think that if you take 1 trillion photons and focus it down to a micron or so, you couldn't control at all what's going on in matter. But in fact, we find that we can control how the matter responds by tuning the photon energy of the X-rays and by tuning the pulse duration in which you deposit those X-ray photons into the atom.
So tell us about the experimental setup, just briefly. What did you actually do?
Okay, so you take this very intense X-ray beam and you focus it down to about a square micron into a jet.
That's a millionth of a metre we're talking here, isn't it? So a thousandth of a millimetre across.
That's right. And when you do that, you surround that interaction region by a number of detectors that can detect all the products of the reaction. And so you can detect all the ions that are produced and all the electrons that are produced. And by having these very high-resolution detectors, you can tell exactly the mechanism by which the neon atom becomes stripped of its electron.
So you fire these very intense X-ray beams into, a cloud of atoms, and you say neon, so that's a noble gas, isn't it? Very unreactive. What happens to the atoms when they're hit with this very intense burst of X-rays?
Well, that depends on what photon energy you've selected. You can select a photon energy where you hit out the inner electrons first, or you can select a photon energy where you just peel away the outer electrons. So depending on where you are in photon energy, you can do one or the other.
And how does this inform our understanding of physics and our understanding of atomic structure?
Actually, what it informs you of is how very intense X-rays interact with matter. Before this X-ray laser was available, you were only ever able to knock out one of the inner electrons in a shot. But now with this very intense X-ray laser, you can knock out both of the inner electrons simultaneously. And that leaves you with this so-called hollow atom or cord atom. And that hollow atom has different properties than a normal atom, including the possibly advantageous property that when the inner electrons are missing, then the X-ray absorption is decreased relative to the scattering cross-section. And the scattering cross-section is what forms an image for you to make further molecular movies or images of complex molecules. So what I would say is that we're just exploring a new regime of X-ray interactions with matter.
Which is, of course, going to give you the opportunity to begin to understand and probe whole molecules at a kind of resolution in a way that we've never seen before. Linda, thank you very much. That's Dr. Linda Young, who is from Argonne National Laboratory, and she's published that work in the journal Nature this week. And if you'd like to find out about any of the news stories that we're covering this week, we've put the details and the write-ups of those items and the references on the Naked Scientist website at nakedscientist.com/news.
Bringing the facts to bear. The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith and with Kat Arney.
If you would like to contact us through Twitter, it's @NakedScientists, or you can send an email to chris@thenakedscientist.com. Now, we are looking at volcanoes this week. Still to come, we'll find out how measuring tiny changes in gravity can tell us what a volcano might be up to. But first, we're joined by Dr. Chris Kilburn from University College London. Now, he's doing something that may be only associated with James Bond baddies or Dr. Evil. He is drilling into a volcano. Now, I take it, Chris, you're not making a secret underground layer, but tell us about this volcano. Where is it? Why is it interesting? And why are you drilling into it?
Well, because we're arranging to take over the world with our secret schemes, clearly. No, Campifiguré is a caldera. It's a large volcanic complex immediately to the west of Naples in southern Italy. And rather than your typical pointy volcano, it's actually, when you arrive there, it looks like a flat plain, which is then dotted with small cones across its 12 kilometres diameter. And it formed about 15,500 years ago after a large eruption released several tens of cubic kilometres of magma, and the ground simply sank into the hole that was left behind. Why we're interested in it in particular is because the Campifiguré, the west part of Naples, is actually inside the caldera, and there are another about 250,000, 300,000 people in the surrounding districts also living within the caldera itself. And for the past 40 years, it has shown significant signs of unrest. So the central part of the caldera, a town called Pozzuoli, or rather a port, today now has risen 3 metres with respect to where it was in the late 1960s. And so there's some concern that this may be one signal that an eruption may be imminent meaning sometime within perhaps the next 100 years or so.
Crumbs. So you're drilling into a volcano to find out more about it. Tell us a bit about how you go about drilling into a volcano, and then the sort of things that you're looking for once you've done your drilling.
Well, the type of drilling is fairly similar to technology, is very similar to that used for drilling for oil. Of course, perhaps that's not the best analogy used right now, but nevertheless. But what we're particularly interested in is obtaining material down to depths of about 4 kilometres. The reason for that is because all the data that we have so far suggests that the unrest is being driven by changes somewhere at depths up to 4 kilometres below the surface. And we need samples to do experiments on to better understand the physical properties of the rock so that we have a better understanding of how it is likely to break as the whole crust continues to deform.
And what sort of changes are you looking for? What can you tell about a volcano, what it's up to from looking at these samples?
Well, the samples themselves, really what we're going to look at are, for example, the conditions, the stresses that have to be applied for them to break, how cracked they already are, whether it's possible for water to easily pass through the rocks. All this information is needed to interpret the seismic signals that we record normally at the surface, and also to interpret, for example, changes in the ground deformation, changes in gravity signals, as we will discuss later. And at the moment, we have to make best guesses for some key parameters, and hopefully, thanks to the drilling, we will be able to be much more precise about the numbers that we stick into the models.
And the one thing that concerns me slightly is that you're drilling into a volcano. Is it safe? Is there any risk that you're going to sort of, I don't know, wake it up or something?
No, we don't think so, not in this particular case. All the evidence points to the fact that there isn't any significant molten magma right now at shallow depth. What's happened is that if magma has been evolved, it's been small bodies of material that have pushed up to shallow levels, and they've now solidified. In any case, the diameter of the borehole is only a few tens of centimetres across, and it's extremely unlikely that magma will be able to force its way up from 4 kilometres up to the surface, even if we happen by mistake to actually meet some molten material, but that's really unlikely.
One of the things that we know in volcanic areas is that you can harness the heat from the volcanoes and use things like geothermal energy to heat up water. Is that something that you're looking at that you could apply to the Campi Flegrei?
Well, we will take advantage of that. Having drilling the borehole did have more purely scientific and hazard-related motives. But you're quite right. Since once the hole has been made, it will be possible to look at the potential of hot water to percolate through the rock and be utilised for extracted. The heat can be extracted from the water, and then it can be used for energy purposes. In the early 1980s, this was tried once before, but the price of oil was so cheap in those days that it really wasn't economic to develop as a geothermal field. Of course, the economic conditions today are quite different, so it may turn out that this particular borehole will also be used to evaluate whether it's worth developing the area for as a geothermal resource.
How times have changed could be handy. And finally, how similar is the Campi Flegrei to other volcanoes around the world? Can you apply what you're finding out to other volcanoes and make predictions about them as well?
Well, there are several hundred caldera complexes across the world, and somewhere of the order of 130 to 150 have been restless in the last 300-400 years. So we certainly expect that we'll be able to take some of our results and apply them more generally across the world. Other examples include Long Valley Caldera in California, maybe Yellowstone, also in the United States, and Papua New Guinea, the Rabaul Caldera, so to name just 2 or 3.
And not scoping any of them out for a secret underground lair.
Oh, but I couldn't possibly tell you that on air, could I?
Thank you, Chris. That's Chris Kilburn from University College London.
Kat, thank you. This is The Naked Scientist with Chris Smith and with Kat Arney. We're talking about the science of volcanoes this week. If you'd like to join us, chris@thenakedscientist.com. Now, the key to understanding the behaviour of a volcano must lie, partly at least, in understanding the plumbing system that brings magma from deep inside the Earth up to the surface so that it can erupt. And one way to do this is to observe the changes in the gravity field that occur over a volcano. And to explain more, we're joined by Dr. Hazel Reimer, who is from the Open University. Hazel, welcome.
Hello.
Thank you for coming to join us on The Naked Scientist. First of all, tell us, how on earth do you use gravity to plumb or work out the plumbing of a volcano?
Well, good question. It's not the most obvious thing to do, is it? Well, We use a very expensive piece of kit called a gravity meter. It looks a bit like an old car battery. It's a box with knobs on.
Sounds technical.
Very technical and very unimpressive. But they cost several tens of thousands of pounds, actually. And what they are, basically, is a mass on the end of a spring inside them. So it's a bit like the scales that you might see in any market. And instead of sticking 2 or 3 apples into the scale pan and then the spring will extend and a dial will move telling you how far the spring is extended, that would tell you the weight of the stuff in the pan. And what you're doing there is you're changing the mass, as in you're changing the number of apples in your pan, but you're keeping G, the acceleration due to gravity, constant, or you're assuming it's constant. What we do with the gravity meter is we keep our number of apples in our pan constant. In fact, in this particular case, it's a tiny, tiny little mass, about a gram or so. And what we're doing is, in a way, looking for how much the spring extends or doesn't extend in different places as we move our gravity meter around the volcano. And the variable in this case is not mass, as in number of apples, but it's little g, the acceleration due to gravity. So what we're doing effectively is seeing what the weight of our little scale pan inside our gravity meter is as we move around the volcano. And all you have to do is put it into your backpack and wander around across your volcano and set up a series of stations. It could be anything between 10 and 100 points on the volcano, and you measure gravity at them. And
presumably use GPS so you know you're using the same or measuring the same spot.
Exactly
each
right.
time.
Yes. Well, there are several ways of doing gravity actually, and yes, you always do need to use GPS to locate yourself. But one way is simply to end up with a map of gravity. So just as you end up with a contour map that would just tell you the different heights in a particular area. So the lines would represent equal heights. And, if you have lots of them very close together, then the terrain is very steep. That's a topographic map. You can have a gravity map that tells you how gravity varies with space. So, for example, at the top of a volcano, you might find that there was what we call a gravity anomaly, where gravity was particularly high or particularly low, as the case may be. And you would see that by very close together isogals, which are the contours related to gravity. But the other thing is to see how gravity changes through time.
That's what I was going to say, because why should the gravity of a volcano change? Presumably it's gaining mass from somewhere, and that presumably is magma rising into or exiting the volcano, and this will affect how much it weighs, to use a horrible term in physics sense, but it will affect its gravitational attraction for your box.
Yes, exactly right. There are a lot of other things that you need to check, and of course that's why you use GPS and other methods, because if the volcano inflates or deflates, Chris was just talking about Campiflagre, which is sometimes it sinks down and sometimes it rises because it's a caldera in a state of unrest. But for example, as a caldera deflates, as it goes down, you on the surface of the Earth actually get closer to the centre of the Earth, and that means that gravity will increase. So you have to be able to correct for that effect. Having done that, then any net change in gravity that you measure must be due to subsurface mass changes. And in the case of an active volcano, you would probably interpret that in terms of magma movements.
But getting back to the point you made, which is the time one, many observations that are made of volcanoes are not made longitudinally. People don't go back to the same spot year on year on year and then get an accurate record of how that thing is evolving, obviously not on a geological timescale, but on a human timescale. Is that something you've been able to do then? Because you've been doing this for, I was looking at your publications, actually, it goes back 20 years.
I know, it's just that I'm old.
I wasn't going to say that, but...
It is unusual to do it, yes. And not very many people have the opportunity and the privilege to keep revisiting several volcanoes for a long period of time. And actually, you do have to look at several volcanoes because most of them don't do anything most of the time.
Geologists must need to live longer. You need some of those genes that make you live to be 100.
Yes, that would be useful, wouldn't it? You still wouldn't live as long as a volcano, unfortunately.
Ideally not. But so you've been working in Iceland. This blessed thing, that I'm not going to try and say the name of it, but perhaps you can for me. But what have you found there? OK,
well, I've not been working on Eyjafjallajökull itself. I've been working on a volcano slightly further north than that, and it has the advantage of not being covered up by an ice cap at the moment, so it's much easier to measure. And what I've been doing, well, first of all, I set up a gravity network on the volcano to look at the general structure of the volcano. So I had a gravity map, as I described earlier. So it started with that. And from that, and of course the work of lots and lots of other people, we were able to see what the general structure underneath the volcano is and where the magma chambers are. So as Chris was talking about at Campi Flegrei, we think there are several pods of magma underneath the Campi Flegrei. At Aschia volcano, which is the one I've been looking at, it's more or less in the centre of the country. We think that there's a chamber or a storage reservoir of magma at about 3 kilometres depth, and another one a little bit further down. So we worked that out with, among other things, the gravity surveying, and then going back to each of those stations year after year after year, as you say, and making corrections for the amount the ground has been deforming. We've been able to see that over the years, for the first 17 years of the study, there was a net mass loss at the volcano. So, in fact, what was going on was the ground was going down. It was deflating since the last eruption in 1961. And it looked as though magma was draining away from the volcano. And that seems to have been what was going on until about 2007. After that, the seismic activity changed a little bit. And there was a lot of seismic activity, quite shallow, to the north of Aschia volcano. And it was unclear from seismic activity, you can tell that magma is moving. You can't necessarily tell which way it's going. And our gravity measurements suggested over 2008 and 2009 suggest that we've actually got an influx of magma coming back into the volcano. So the mass underneath it has increased, which is quite exciting.
Do you think that the activity we've seen this year in its partner, the one I can't say, do you think that's relevant then to this? Do you think that one could be a symptom of the other, if you like?
Well, never say never, but I don't think there doesn't have to be a connection. The volcanoes the volcanoes are several tens of kilometres apart from each other, and of course the plumbing system is linked at huge depth, but they have separate feeder systems. So I don't think that there's likely to be a connection.
And just to finish us off, Hazel, does the data that you've generated here inform our understanding of how volcanoes behave in general? In other words, does this tell us a bit more about what predictions we can make about their likely evolution over both human and geological timescales?
Well, I hope so. Otherwise, I don't know why I've been doing this.
You may have got negative results. I don't know. But, I mean, you obviously haven't. But
well, yes, I think it does. But again, as Chris was saying earlier, there are lots of different types of volcanoes, and he talked about the sort of pointy peak volcanoes and the flat ones and the ones that are basically a hole in the ground. There's a huge variety of volcanoes, and they all work in slightly different ways. There are a lot of variables to do with the thickness of the lithosphere, the crust that they're coming up through, the chemistry of the magma. Sometimes it's very thick, sticky stuff, so it's harder for it to move around. There are a huge number of variables, and you need to understand all of those variables to be able to put together a sensible picture of how an individual volcano is working.
But you've made a start, and that's the most important thing.
I've had a go.
Brilliant. Thank you very much. Hazel Reimer from the Open University.
Still to come, we find out how mixing coke with wallpaper paste makes a good model of a volcano as well as a colossal mess. That's in this week's Kitchen Science Experiment. And in Question of the Week, we find out why using an electric toothbrush can make your screen go wobbly. If you're interested in volcanoes and rocks in general, as we've been talking about today, you might want to try out the OU Interactive Geology Toolkit. It's an online resource where you can explore the rocks that make up the British Isles. You can use a rock analyzer tool to identify the rock samples that you found. And to have a look at that, you can visit thenakedscientist.com and just follow the links that we've got there on the site.
Kat, thanks very much. We are talking, as Kat said, all about the science of volcanoes this week. And to help us forecast an eruption, we need to understand as much as possible about the processes that cause a volcano to form in the first place. And we're joined now by Professor Gillian Folger, who works on understanding how volcanoes form in places like Hawaii. Gillian, welcome.
Hello, Chris.
Welcome to The Naked Scientist. Tell us, if you would, first of all, how do volcanoes form and what are the areas of contention?
Well, most volcanoes in the world occur along the edges of tectonic plates. So most people are probably familiar with the concept that the Earth's surface is broken into lots of plates like the shell of a tortoise. And along their edges, where they move past one another, there are huge cracks going right through the bathysphere down into the asthenosphere below, and molten material can leak up through these cracks and form volcanoes. So the volcanoes such as Mount St. Helens and the Cascades volcanoes, the volcanoes at Japan, they all occur along plate boundaries. But there isn't too much controversy about how they form, but the real controversy lies with the volcanoes that form smack in the middle of plates. Where
Can you give us some example of those?
Well, an example is Tristan da Cunha, Reunion, Iceland. People also, interestingly enough, put Iceland in that category, and of course Hawaii.
Okay, so these are volcanoes that pop up in the middle of a plate. So what goes for at the margin of a plate, or a plate boundary, cannot go for what's going on in the middle. So what do scientists think is driving the emergence of a volcano at that point then?
Well, there are two competing hypotheses. There's the plate hypothesis, which says, hang on, plates are not completely rigid. That's just like a cartoon world. What geology is much more complicated than that. And huge plates, they do have cracks, they do pull apart in their middles, and we can have the occasional volcano that comes up through a crack in the middle of a plate. And the competing hypothesis is the traditional plume hypothesis, which suggests that you have a hot diapair, hot thermal coming up from the Earth's core, rising 3,000 kilometers through the Earth's mantle and punching its way through the plate at the surface, not caring whether it's in the middle of a plate or not.
Have we any idea as to why such a pulse of energy should be unleashed by the core in that way? Why should that happen, and why don't we see this more extensively then?
Well, that's a very good question, Chris, because you often hear people say Hawaii is a typical example of a plume. But in fact, Hawaii is completely unique on the Earth's surface. There isn't anything else like it anywhere. But coming back to your original question, why should this happen? People have pointed out that the Earth's core is about 1,000 degrees hotter than the material immediately above. So they have this model like a kettle on a stove with a hot plate underneath, and the hot plate is heating the water in the kettle and causing diapirs to rise up. So that's the fundamental concept behind that theory.
So it's almost like a weak spot, and the energy gets focused somewhere, and as soon as something gives, then it gets channeled up through whatever that weakness is, and that just happens to be, say, Hawaii, or there must be other examples of these plumes, like the ones you gave, where this energy is unleashed. But how can we resolve that question? How can we study this? It's not trivial to get into a planet that's got a radius of 6,000 kilometres and find out what's going on in the middle. How can we address this problem?
One of the primary methods used is using earthquake waves to CAT scan the Earth. So when earthquakes occur, rays go through all parts of the Earth, and we have seismometers on the surface. So this is like taking a person in a hospital and CAT scanning, and we can look at the structure inside the Earth. And what we're really looking for is to see if under places like Hawaii and Iceland, if we see some kind of a structure going all the way from the surface right down to the Earth's core. And if we saw that, that would pretty much be strong evidence in favour of the plume hypothesis.
So what have you seen? You presumably haven't seen that yet, so what have you seen?
No, what we tend to see almost everywhere is structures which can go down several hundred kilometres, but they don't go down the full 3,000 kilometres that they would have to do to reach the core.
So do you think it's just a question of making more observations, or do you think we need to rethink this model and in fact you don't need to go all the way down to the core? Perhaps it can act as a sort of vent for pressure slightly outside the Earth's core?
Yes, I think we don't need to go down to the Earth's core. I think everything is happening just in the upper 300, 400, 500, 600 kilometres. It's not going all the way down 3,000 kilometres to the core. But regarding how do we address this problem, well, part of the reason why this controversy is so exciting is because a lot of human aspects are weaving in which almost stand outside science. The plume hypothesis has been popular for a very, very long time, and there's great reluctance to let it go, partly because it can sort of be trotted in to explain everything. Whatever you see or you don't see, you can find some way of turning the plume hypothesis around to explain that. But the plate hypothesis, on the other hand, makes specific predictions which we should be able to go out and test. So there's great excitement in the geological community at the moment, and some people say this is the most exciting and fundamental controversy that's developed since plate tectonics.
So obviously, we will be in a position at some point in the future to make reasonable predictions about volcanic activity at plate margins where one plate is either subducting or overriding another. But if we've got this problem with plume volcanoes, how can we predict those? If we don't understand what's causing them in the first place, how can we predict their activity? This
subject is really looking at big-scale and long-term volcanic behaviour. So unlike what Hazel was describing, Hazel is looking at the activity of specific volcanoes on the kind of time scales that are relevant to human beings, a few years or a few decades. But we're looking at the big scale things, and we're looking on time scales of millions of years. So the sort of problem we would be interested in, for example, that we could contribute to would be when Kilauea in Hawaii becomes extinct, where is the next volcano going to form?
And presumably also you're in a position to inform the climate change debate, because we know that volcanoes and volcanism has had a big contribution to the Earth's atmospheric composition over many, many years, and understanding this important contributor must therefore also feature quite heavily in the argument.
Yes, it would certainly give relevant data to that subject, indeed.
We must leave it there. Thank you, Gillian, for joining us. That was Professor Gillian Folger, who is at Durham University.
Laying the facts bare. I say. The Naked Scientists.
This is The Naked Scientists with Chris Smith and with Kat Harney.
If you'd like to get in touch, you can contact us through Twitter. It's @NakedScientists. And you can send an email to chris@thenakedscientist.com. And now, with an experimental explosive eruption, here's Ben Valsler.
For this week's Kitchen Science, we have a very special guest with us. That is Professor James Jackson from Cambridge University's Department of Earth Sciences. And he has an explosive experiment to show us. What do you have prepared?
What I have prepared is some Coca-Cola bottles which have been doctored to make them indeed explode more in order to mimic what happens in volcanic eruptions which produce big, high eruption columns.
So how have you doctored the Coke to make this work?
What I've done is made it more viscous, or if you like, less runny. What matters in volcanoes is how runny the liquid is that's trying to get out of the volcano. That's viscosity, and there are two types, essentially. There are volcanoes which are in the oceans, such as Hawaii and Iceland, where the magma is very runny, and that can escape from the volcano very easily and doesn't cause any trouble. The other sort is more common on the continents, especially in the high mountains, places like the Andes, which is much stickier magma trying to get out, and that causes trouble. Now, the reason it causes trouble is because magma has water dissolved in it, and you want to think of the water as a gas, essentially, and it dissolves in the magma rather like the carbon dioxide dissolves in a Coca-Cola bottle. So when it's under pressure, you don't notice it, it's just in the liquid. And the problem comes when the gas tries to get out as you get nearer the surface and the gas forms bubbles. Now, if the liquid is runny, if you take the top off an ordinary Coke bottle, the stuff is runny enough for the bubbles just to froth out. You get a bit of froth, but the bubbles can escape. If you have a very sticky magma, what happens is the bubbles appear because the pressure is less. It's like taking the top off a Coke bottle. You'll always get the bubbles. But if the bubbles can't get out, then you're in trouble, because what happens as the pressure reduces is the bubbles get bigger and bigger and bigger, and they still can't get out until eventually they join up. And when they join up, it stops being a liquid with gas bubbles. It turns into gas with bits of liquid around, and the whole thing explodes. And that process is called fragmentation in magma. That's what the volcanologists talk about. They talk about the magma literally being ripped apart by the gas bubbles joining up and just escaping like a jet and pulling everything apart.
So it's important that there's still lots of gas in the Coke when we try this?
Yes. What you have to do is make the Coke stickier. So what you do is put wallpaper paste in. So you pour off a little bit of the Coke from the top of the bottle, fill it up with wallpaper paste, shake it a lot, and the whole thing will actually go almost solid like a jelly. And that is what we've done to make these things stickier. It's still got the gas in there, and the gas is still trying to get out, but it's trying to get out through a sticky liquid instead of a runny liquid.
I notice that you've got the bottle stored in a bucket of warm water. Is that helpful?
This is a detail, yes. What actually I'm trying to do there is, to begin with, when I took the water out, the top of the bottle off, it was cold, and I did that to try and keep the gas in. So the gas is more soluble when it's cold, and then I've made it stickier. And now, because I want actually the gas to come out of solution, I'm warming it up, because that makes the gas want to try to come out of solution even more.
Now, you seem very well prepared. You've laid out lots of newspaper and you're wearing a poncho, so obviously this could get quite messy.
Don't do this indoors.
OK.
No. OK, so we'll try it and see what happens, if you like. So here I've got this thing, and as you can see, it's hardly runny at all. It looks like jelly, essentially, in a bottle. You can't really pour it. So I'm going to stick it here in a workbench, something just to hold it, and I'm going to take the top off, and you'll see what happens.
I think at this point I might step back. So we're going to take the top off. It almost looks like a bottle full of treacle rather than Coke.
So it's still coming out. So normally if you take the top off a Coke bottle, it would, you'll get a bit of froth and that would be it. But here this stuff is still coming out because the gas is still driving the magma out as the gas pulls it through, because the gas is still trying to get out and it's having a hard time because the thing is so sticky.
Now, it's taken on a very different consistency. In the bottle, it looked thick and gooey, it looked treacly, but now it looks more like honeycomb.
That's the bubbles, and the bubbles can't get out, so indeed it looks a sort of mottled colour. It's mostly air that you're looking at with a little bit of liquid. And that's what pumice looks like. That's what pumice is in volcanoes. If you ever pick up a piece, pumice is about 80% air. It floats on water. So it really is, it looks like sort of fiberglass. It's mostly air with just a bit of the magma solidified as glass. And this is sort of what this looks like.
We have one more bottle, so should we give it one more go? Normally, when we've done explosive cola bottles experiments before, you end up with a large puddle, but this stuff has really piled up.
Yeah.
And I'm assuming this is how volcanoes lead to that distinctive cone shape on the top.
That's absolutely right. So that the runny volcanoes don't really look like a conical shape at all. They're what are called shield volcanoes. They look like a very gentle slope because the lava can flow maybe 100 or 200 kilometres easily. But this stuff is very sticky, so it doesn't go very far, and that's what gives you the conical-shaped volcanoes. So the famous cone-shaped volcanoes people have heard of, like Mount Fuji in Japan, are made from this sticky stuff.
OK, well, I will step back again. We'll open one more. Well, I now have Coke lava on my jeans, my shirt, and unfortunately on my microphone as well. But that one was really explosive. So as well as enabling the volcano to build a cone of this pumice, this also, as we've just seen, can enable it to throw material quite a long way.
Yes, that is the key to understanding how this works. It's the gas coming out very, very fast, which allows the column to go so high in the air. Right, it's coming out of the volcano about the speed of a jumbo jet, and if you just took a jumbo jet and threw it in the air, it would go about 2 kilometres high. These things go about 20 kilometres high, and the reason they go so high is they're coming out so fast, they suck in the surrounding air. And they're not only coming out fast, but they're hot, so the surrounding air gets heated, and the whole thing becomes buoyant, much lighter than it would otherwise be, which allows it to rise much higher in the atmosphere. So that is the trick for getting them so high.
Well, we had better go and get cleaned up before the wallpaper paste in this glues us together. And that's all we have for Kitchen Science this week, and we'll be back with more very soon.
So, cola mixed with wallpaper paste to make it more viscous is a very good model for the viscous lava flow that we see in certain types of volcano. And when you open the bottle, the huge explosion fires globs of cola lava high up into the air and all over the place, and then it oozes for several minutes afterwards. That was Professor James Jackson from Cambridge University's Department of Earth Science showing Ben Valsler a particularly messy kitchen science experiment. And we've put pictures and video of their rather explosive experiment online at thenakedscientist.com/kitchen science, and you can find many, many more experiments there that you can try at home.
And the experiment really is very messy, and the video is well worth watching, I can assure you. Thank you, Kat. This is The Naked Scientist with Chris Smith and Kat Arney. We're joined this week by Chris Kilburn and by Hazel Reimer, two experts in the world of volcanology, and we have got a huge number of questions. Let's kick off with you, Chris. Don JX on Twitter says, how many volcanoes are there around the world in total that are non-dormant today?
Well, Chris, there are about 600 to 1,000 volcanoes for which we have records of eruptions. They've actually been observed. But using radioactive dating techniques and what have you, we think there are about 10,000 that have been active in the last 10,000 years and have the potential to erupt again.
Gosh, large numbers. Hazel, Mohammed Y on Twitter says, can volcanic eruptions substantially change the climate? More so, for instance, than man-made activities?
Well, it does depend what you mean by substantially change, but and what sort of eruption. But yes, some of the largest volcanic eruptions have profoundly affected the climate and could do so again in the future.
Thank you. I think there's evidence that the legacy of Krakatoa from 1880 is still there in the sea. The ocean level is still a bit lower than it would otherwise have been because the Earth cooled because of the stuff ejected into the atmosphere, isn't it? I think it's a paper published in Nature a few years ago on that, wasn't there?
You can see these effects for an extraordinarily long period of time, yeah.
Next question. It's like 100 questions. NSB UK 001 on Twitter says, what exactly are pyroclastic flows and what makes them so deadly? Who wants to have a go at that?
Okay, well, pyroclastic means literally broken by fire. It means broken up and exploded rock. So when a volcano explodes, it forms a pyroclastic flow. And what's so nasty about it is that they are often very, very hot, and they are clouds of very hot ash that go billowing very, very rapidly along the ground, engulfing everything in their path. And if you've ever been to Pompeii or Herculaneum and seen the devastation, that's why they're so dangerous.
Terrific. Mikey, MYKIE213 on Twitter, @NakedScientists, if you want to send us a Twitter, it says, is it true that volcano locations, after they've run their course in one spot, move forward to another ahead? Chris?
Sometimes it appears to be the case. For example, Julian Folger mentioned Hawaii and other mid-plate volcanic chains where there is evidence that the activity migrates in a particular direction with time over a geological timescale. Other volcanic areas, you don't actually see the same process. So it can be observed, but it doesn't have to be.
Thank you, Chris. Bao who's listening to us in Second Life, hello to all of you, says, is the centre of the Earth entirely full of molten material or is there some gas? It's a bit like a, say, half-full bottle.
Well, there's no gas right inside the centre of the Earth because the pressure is much too high. It only comes out as gas when it finally gets to the surface.
So what is there? What is the structure of the inside of the Earth? Where is the magma?
Well, the magma that comes out of a volcano is really only sourced several kilometres beneath the surface. I mean, it's really just beneath the skin, effectively.
Hazel, thank you. Here's a hard one. James Townley says, what is the largest active volcano in the solar system? Chris?
Well,
in the solar system.
Well, to be honest, I suppose, because active means we have to have seen it erupting, we have evidence that it was likely to, I guess we still have to stick with the Earth, of course, and so that would be Hawaii. But volcanoes such as Olympus Mons on Mars, for example, are considered to be the largest volcanic edifices in the solar system. And some of the Jovian satellites, there is evidence of volcanic activity, but I'm afraid I don't know how big those volcanoes are. So I think for that time
Olympus
being...
Mons is something like 22 kilometres high. It's big,
yes, Mars. I meant the ones out around the satellites of Jupiter and what have you. But certainly, I think we'll stick for Hawaii now. Of course, the Martians, we may have some interesting activity should we ever finally set foot on Mars. We never know.
Thanks, Chris. Hazel, can you do in 20 seconds Bauer's question, if magma leaks out, is there empty space left where the magma was?
No, luckily there isn't. There's plenty more stuff to replace it.
Thank you very much. Hazel Reimer and Chris Kilburn, our two volcanologists with us. Thank you for doing an amazing job at so many questions so very quickly. Well, now it's time for our question of the week. Here's Diana O'Carroll.
This week, things you can do whilst brushing your teeth for the full 120 seconds.
When I brush my teeth with an electric toothbrush, my vision remains normal. However, if I look at a computer screen or digital LED clock, the image is shimmering. Why the difference?
So what is happening? Is your head wobbling in time to the display?
My name is Mikael Karlberg. I'm a consultant and associate professor at Lund University Hospital in Sweden. It's an interesting question, but I noticed that phenomenon like 10 years ago also while brushing my teeth and watching television on the same time. And I thought, this is very funny. And then we did some just experiments in front of computer screens, making like a farting sound with your lips and watching the screen on the same time and seeing exactly the same visual phenomenon. And then I'm specialized in inner ear disorders and disorders of balance. We started to study the inner ear receptors, the vestibular receptors, that is the perception of vertigo. And the sensory cells are really small sensors that are sensitive to vibration, just like the auditory hair cells that make us hear. But it turned out, as I found experiments from the 70s, that if you vibrate the skull and measure what the vestibular receptors do, they phase lock to the vibration, so they start to signal with the same frequency as the vibration that is applied to the skull. So if you vibrate like with 100 hertz, the vestibular cells start to fire at 100 hertz. So what I believe happens here is that we watch a screen, and the screen is updated around 50-60 hertz, 50 to 60 times every second. And then we apply a vibratory stimulus to the vestibular hair cells, so they start to fire at a different frequency. And what we really notice here is some kind of interference phenomenon between the updating frequency of the screen and the vibration applied to the sensory hair cells.
And what those vestibular system hair cells are actually doing is controlling your eyes so that the eyes move in the opposite direction to the movements your head makes. Now, this is normally very important to help you to see objects clearly, even when your head's moving around. But the vibrations from the electric toothbrush can disturb this control, which makes the eyes move unnecessarily, and consequently the LED clock or the television or whatever you're looking at, which is turning on and off very quickly, gets stroboscopically caught by your moving eyes, the visual system, and the numbers appear to flicker.
Next week, who wins the technological prize?
Hello, naked people. My name is Levi, and I'm calling from Israel. Recently, I came back from a trip in South America. My question is, why is it that in the time of the discovery of the Americas by Europe had the Renaissance, Leonardo, guns, steel, and so on, while the Americas were stuck in a sort of Bronze Age? Was the reason geographical, nutritional, religious? What? Love you all. Thank you. Bye.
Why wasn't the old world discovered by the new world? Let us know what you think by emailing chris@thenakedscientists.com or by writing on the forum, and that's at thenakedscientists.com/forum.
Thank you very much. Diana O'Carroll with our Question of the Week, and you can find out the details of all of our previous Question of the Weeks on our website. That is, unfortunately, all we have for you this week. Next week, we're having a look at the role of lasers in medicine, how they can be used to treat diseases and also to do groundbreaking research. So if you have any questions about the science of lasers, then you can send them in to me. It's chris@thenakedscientist.com, or you can tweet @nakedscientist, or you can even post a question on our Facebook page, or even join the discussion on our web forum. That's nakedscientist.com/forum. Many thanks go to Linda Young, to Hazel Reimer, to Chris Kilburn, Gillian Fulger, and James Jackson for joining us this week, and also to our wonderful production team here at The Naked Scientist, Mira Senthilingam, Diana O'Carroll, Sarah Caster-Perry, Tom Simpkins and Ben Valsler. The Naked Scientist was produced and presented by me, Chris Smith, with Kat Arney, and it was produced in association with the Open University. To discover a whole range of science content, including lots of interactive features, you can log on to thenakedscientist.com and follow our links through to the Open University. Thanks for joining us, and see you next time.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.